welcoming of the new members elected last year. Of course, we elected a bunch of new members also yesterday and this morning, but their name will appear later. But last year, we elected a number of new members. Many of them have come here for the conference and for today, and we are going to greet them, and that will take place in, of course, most members, like in academies, when they are elected, they feel the honor and they are pleased. Some of them will also be active in the academy, and my hope is that a number of the newly elected members will not only be honored by becoming a member, but that they will continue to be a member, an active member, in the years to come. So that's my wish and hope for the new members, that they will really be active in the activity of the academy. So now I'm going to the front, and sorry.
As mentioned by the President, welcoming new members is extremely important for our academy, like for every academy in the world. This is really a highlight. And we are very happy that today 45 new members have come to beautiful Barcelona. And Andre has just highlighted a very important element of Barcelona. But there are, of course, many more reasons to come to Barcelona. And I think it is very special, of course, to welcome them here in this beautiful hall. The names will be announced, and they will come forward up front to receive the personal congratulations by our President. And we will have a number of cohorts which are grouped according to the sections they have been newly elected. And as the President just mentioned, we of course count on them for the future of the Academy. As was stressed by Andreu, there is a strong future for Europe and for this Academy, and of course they are a very important part of this future. And we all hope that today will be the first day of the rest of their life, that they will go home with very good memories to this event. So I would like to call upon the first group of 4 distinguished new members from the History and Archaeology section, the Classics and Oriental Studies section, and the Linguistic Studies section. And this concerns from the History and Archaeological section, Richard Stemplowski. Please come up front. New member in the Classics and Oriental Studies section is Colette Bordelot, and for the Linguistic Studies section, it concerns Bonifakas Stungia and Bo Rolf. Please take the floor. And I'm very happy to see that you immediately give them a hand. So, congratulations. And of course, the picture. Thank you. We move on with the second group, and these are members of the Literary and Theatrical Studies section, Musicology and History of Art and Architecture, and Philosophy, Theology and Religious Studies. And I would like to invite Martin Middeke and Wang Nin, who came all the way from China, very much welcome, to come up front. Congratulations. Then I would like to invite Emilio Ros Fabregas, new member of Musicology and History of Art and Architecture. Thank you. And then I would like to invite the new members for Philosophy, Theology and Religious Studies, Jan Wolinski and Joel Biar. Okay, please. Then we move on to the new members of the Social Sciences section. 4 new members have been elected, and I would like to start off with the first one, Yale Ferguson. Please come forward. Thank you. Then I would like to invite Salvador Giner. As President Wallø mentioned, all these members have been elected in 2013. We are very happy to have Anders Malmberg here, who was elected in 2012. Especially welcome to you. And finally, Leo van Wissen. Then we move on to the new members from the Economics, Business and Management Science section. These are 5 new members, and I would like to start with Salvador Barbera. Welcome. I would like to invite Laszlo Saba. It is my pleasure to invite Kai Conrad. I would like to invite Friederike Wall to come forward. Please don't forget to look to the photographer. And finally, Amélie Constant. Thank you for coming. Then we move on to the informatics section. They have been extremely active in electing new members, in total 10 new members, and I would like to invite the first group of 5 to come forward. And the first person that I'd like to invite is Henry Ball. Great. Jordi Cortadella, please come forward. It is my pleasure to invite Sagram Dustar. I'd like to invite Carlo Gezzi to take the floor. It's my pleasure to invite Martin Kollenbeek. We continue with more new members of the informatics section, and the first one of the second group is Christian Janssen. Bart Pruneel, please come forward. It's my pleasure to invite Siegfried Selber here. Welcome. I would like to invite Roman Slowinski. And the final, Arnold Smulders, informatics section, please. Thank you. We now move on to the physics and engineering sciences section. This section has elected 3 new members, and the first one is Ergin Atalar. I would like now to invite Michel Gevers. It's my pleasure to invite Gabor Stepan. The next group of 4 are new members of the Chemical Sciences section, and I would like to begin with Enrique Carnedal. Welcome. It is my pleasure to invite Craig Hill. I would like now to invite Roland Nolte. It's a great pleasure to welcome another member elected in 2012, Hans-Peter Steinrück. We move now on to the Earth and Cosmic Sciences section, and I would like to invite Pilar Ruiz Lapuente to come upstage. It's my pleasure to invite Gordon Brown, coming all the way from the United States. The mathematics section has elected as new member Janos Pins. The behavioral sciences section has elected as new member Valeria Tsepe. The biochemistry and molecular biology section has elected 3 new members, and the first one is José Luis Riechman. It's my pleasure to invite Yannis Tsalianidis. Finally, I'd like to invite Annalisa Pastore. The next section is the Psychology and Medicine section, which has elected 3 new members. And the first one is Elias Campo. Welcome. I would now like to invite Siska Wijmenga to come forward. And we conclude this part with Kurt Zat-Lukal. Welcome. This has brought us to the end of the very warm welcome to all the new members. So let's give them again a warm welcome and a hand.
Now that we have had the formal welcome to the new members of the Academia Europaea, we will have a bit of a more informal welcome also. So I'm inviting Professor Josep Domingo Ferrer from the Informatics section, who's a relatively new member of the Academia Europaea, elected 2012, and he wants to say a few words.
Hey, good evening, President of the Academia Europaea, President-elect, Honorable Professor Andreu Mas-Colell, Minister of Knowledge and Economy of the Catalan government, Professor Enric Banda and other Professor Joan Domènec Ros and other authorities. Especially welcome to the new members of Academia Europaea in this session. Having been myself elected a member in 2012, I still remember well what it takes to be a member of Academia Europaea and how different this academia is from other institutions of similar nature. First of all, it is an academia of sciences and humanities. So there are few fora where scientists and social scientists and humanities researchers can meet, and here we have one of these places. It is also an independent organization with over 3,000 members and 20 sections, so it is a powerful organization, and therefore it can have an impact. So when you are elected here, I think that it's a matter of keeping in mind that whatever you do can have an impact in European science policy. And this is, as Andreu Mas-Colell put it a moment ago, this is a civil society organization that is very needed in Europe. Europe is not just a collection of countries and a collection of bureaucratical organizations. It is also a society, a joint society, and this is an example of organization that arises from the bottom and tries to have an impact on the governance of the European Union. So you will be in good company. There are here a few Nobel Prize winners. So it is a prestigious organization, and no doubt you will endeavor to increase its prestige and also have an impact beyond your own field. So I really welcome you in this city of Barcelona, in this academia, and I hope you will enjoy the coming 2 days, and you will use them to cross-fertilize with other colleagues in other areas. So welcome back.
Without further ado, we're going to proceed now to Professor Waller will say a few words about the Bergen Scholarships, and we will proceed with the ceremony. Professor Waller.
Yes. The Bergen Scholarships were established with the name of the first president of Academia Europaea, the UK pharmacologist Arnold Bergen. He was the first president, and it was his special concern that we should try to inspire young scientists and scholars. So the established prizes or the scholarships is for young people in the hosting country. In this case, not only Catalonia, of course, but Spain. So the young people are found by a local committee, and there are 10 such scholarships, and they receive a diploma and a book, and they will speak for a very short period of time, and not thanks and something like that in the presentation. We want to hear about their project. What are they doing? What have they been doing? And that's what I'm going to listen to. I will stand in the front. They will come up, give their short talk, then come and I will shake hand and give them the diploma, and Battimer will give them the book. Yeah.
So the first Bergen scholar is Isabel Angelovsky. So I'm going to invite you to come up here and speak to us about your research for just 1 minute.
So good afternoon. I'm not thanking anyone. I'm just speaking about myself, I guess. So my name is Isabel Angelovsky. I came back to Europe 3 years ago after spending 10 years in the United States doing urban planning work and research, and in particular looking at the inequalities faced by racial minorities, by poor people in view of accessing environmental goods and services. So for instance, the fact that Blacks, Latinos, Pakistanis, name them, are generally less able to have access to good sanitation, to healthy food, to parks. And I've been looking at the strategies and tactics that community groups in the US, in Europe, and in Latin America have developed to enhance the environmental quality of neighborhoods that are generally marginalized and vulnerable. So this has been my work, and most recently, I've been looking at something a little bit more provocative, which is how actually enhancing the environmental sustainability of a city creates more inequalities. Because, for instance, you have a new train station that's supposed to enhance public transit, you create a park, but actually that encourages real estate development and new types of investments that bring in higher classes, and the people who've been there for a long time are not able to stay anymore. So how do you balance sustainability and equity and justice? That's my work.
Almudena Fuster Matanzo.
So good afternoon, everybody. My name is Almudena Fuster, and I come from Madrid, from Professor Jesus Avila's lab in the Molecular Biology Center of Madrid. I've been working there for 8 years, and I got also there my PhD degree in neuroscience for my work in studying the role of GSK3 beta protein in the formation of neural neurons in the brain, especially in the hippocampus, and its relationship with Alzheimer's disease and cognitive and memory functions. Now I'm keep on working there as a postdoctoral fellow, more focused on the role of GSK3 beta and neuroinflammation and its relationship with some different inflammatory molecules. And next year I'm moving to United Kingdom, sponsored by a Marie Curie Fellowship, to carry on my work on neuroinflammation, and this time in the context of stroke pathology. And that's all. Thank you.
David Hernández de la Fuente.
So good afternoon. My name is David Hernández de la Fuente. I'm a classicist, and I'm a professor, an assistant professor at the UNED in Madrid, the Spanish National Distance Learning University. My research focuses on late antiquity, cultural and religious change in late antiquity. I've been working on Neo-Pythagoreanism and Neoplatonism, especially the lives of Pythagoras, of Iamblichus and Porphyrius, of which I published a translation and a commentary recently. And I'm focusing on the 4th and 5th centuries AD, to examine the final confrontation between paganism and Christianism in the model of the holy men, be them Christian or pagan, in the case of Pythagoras, which is my specialty. And I've been working also on the reception of Platonism in late antiquity and in early Byzantium.
Inmaculada Hoyos Sánchez.
Thank you very much. I am Inmaculada Hoyos. I got my PhD in philosophy at the University of Granada with a dissertation on the naturalism and the theory of passion in Spinoza's thought. I am currently a postdoctoral researcher at the Centre Léon Robin de Recherche sur la Pensée Antique, CNRS, Université Paris 4 Sorbonne. My current postdoctoral research analyzes the development of the cognitive evaluative theory of passion in Stoicism, from Chrysippus to Seneca. The core aim of my research is to show that Stoicism is one of the main sources of Spinoza's theory of passions, and to demonstrate that there is a line of continuity between the Stoic concept of pathos and Spinoza's notion of affectus. This line of continuity will coincide with a greater recognition of the dual theoretical and practical dimension of passions. I would like to thank the Academy for this award. I am deeply honored to be awarded such recognition. Thank you very much.
Mark.
Good afternoon, everybody. It's a pleasure to be here. My name is Mark. I'm a postdoctoral fellow at Internet Interdisciplinary Institute, Universitat Oberta de Catalunya, based here in Barcelona. My research interests, broadly speaking, concern socio-environmental relations and the city, and the theoretical framework I use to approach them are urban political ecology and critical geography. And in this sense, I don't understand socio-environmental processes as something external to society, but instead I assume that both are mutually constitutive and remake each other over space and time. More specifically, my research deals with the political ecology and economy of urban water management and water infrastructure. On the other hand, I am also interested in understanding the role the environment plays, both in discursive and material terms, in the workings of new urban models, such as the smart city. So, thank you.
Silvia Pellicer Ortín.
Thank you very much. So I am Silvia Pellicer Ortín. I am a lecturer at the University of Zaragoza at the Department of English and German Philology and the Faculty of Education. As you may see in my poster later, my main research interests lie in contemporary British literature, mainly fiction and semi-autobiographical genres, and I mainly focus on British Jewish writers and mainly women writers. I am also concerned with the fields of memory, Holocaust and trauma studies, and feminism and women's studies. I've delivered papers in several conferences dealing with these topics and published articles on this. I would like to highlight the co-edition of a book entitled Trauma Narratives and Her Story, and a special issue of the journal Critical Engagements on the work of the British Jewish writer Eva Fayez. So thank you very much.
Our next Bergen scholar is Alexander Pondrom.
Good afternoon, everyone. My name is Alexandre Pondrom. I did my PhD in INRS at Quebec, Canada, on electrocatalysis and supercapacitors. And I'm currently working as a postdoctoral fellow at the Institut de Ciencias de Materiales de Barcelona. mainly focusing on electrolyte for sodium-ion batteries. So basically, sodium-ion batteries, very quickly, is based on the similar chemistries than the lithium-ion batteries, but we try to replace lithium by sodium, and therefore trying to make this technology much more cheaper and sustainable, since this is the sixth most abundant element on Earth. Thank you very much.
David Sánchez Ruenes.
Thank you very much. I'm David Sánchez Ruenes. I got my PhD in computer science by the University Polytechnic of Catalonia. And I'm now a lecturer at the computer science department in the University Rovira i Virgili, which is about 100 kilometers in the south of Barcelona. And I'm with the Security and Privacy Research Group, led by Josep Domingo. And my research is about protecting the privacy of data published in open environments, like, for example, publications in social networks or electronic records of patients or any kind of data that could be interpreted semantically. So the goal of the research is to apply artificial intelligence and knowledge-based techniques in order to make computers to be able to understand the meaning and the semantics of such data, so that it could be protected in a better way, and also to retain the utility of this protected data for readers and data analysts. Thank you very much.
Víctor Sebastián Cabeza.
Thanks, everybody. My name is Victor Sebastian. I am a chemical engineer. After the degree, I moved to US with a Fulbright fellowship to work with Professor Klaus Jensen in the synthesis of nanomaterials with microreactors. These days, I'm assistant professor at the University of Zaragoza, and I'm working as a researcher in the Institute of Neuroscience of Aragon. So my research is focused in synthesis of nanomaterials. So why? Because materials under the nanoscale behaves in a different way than the Bergen scale. So this brings to us new opportunities, new applications. For instance, we can work with these materials in biomedicine or catalysis and so on. So there is a poster downstairs, and I kindly recommend you to go and join to me. And yes, I can give you some further details about my research. So thanks.
Finally, Pedro Serna Merino.
My name is Pedro Serna, and I'm a Ramón y Cajal researcher at the Institute of Tecnología Química of Valencia, and my area of expertise is catalysis, and more particularly the use of small metal nanoparticles to perform chemical reactions in a more efficient and greener way. So what we try to do is understanding how the properties and structure of those nanoparticles affect catalysis, so we can make more active and selective materials, and then develop a process that leave no residues. So thank you.
This is it for the Bergen Scholars ceremony. We're gonna have a break now. It's gonna last about half an hour. You have coffee and pastries, I think, out here. So I invite you all to stay for the Erasmus lecture that will be delivered by Professor Kurt Melhorn. And I remind you that the registration desk will be open during the break in case you want to pick up your registration materials. See you back in half an hour.
We are now going to the Erasmus Medal and the Erasmus Lecture. The Erasmus Lecture and the Erasmus Medal was established by the Academia Europaea more than 20 years ago. It's awarded for significant and long individual scholarship and achievements. And every second year, it's usually in the humanities or social sciences, and every other year, it's usually in the physical or biological sciences. So this year, we have the field is informatics, and we have the chair of the informatics section, Professor Bergström, who will give the laudatio of the receiver of the Erasmus Medal.
Ladies and gentlemen, and members of the Academia Europaea, it is a great pleasure and honor for me to address you on the occasion of the 2014 Erasmus Medal of AE being awarded to Professor Koert Meelhoorn. Please allow me a personal remark to begin with. I was born in Rotterdam, where I spent the first 18 years of my life. In those years, Rotterdam was searching for a new post-war identity. And I can assure you that Erasmus was seen as an icon of intellectual achievement connected to Rotterdam. To this day, Erasmus is seen as probably the most visible, if not most important person ever to be born in Rotterdam. A second personal remark pertains to my role as a chair. In that capacity, I am speaking to you. Each time the Erasmus Medal is awarded, two instances of achievement come to the forefront. First of all, the intellectual achievement of the winner of the medal, which I will discuss shortly. And secondly, the achievement of those who nominated the candidate, arguing the case in a highly competitive field of candidates, all of whom merit this exclusive level of distinction. This year's Erasmus Medal is the first medal to be awarded to a member of the informatics section. Naming our field in a stable manner is not so easy. A classical term is computer science. Without hesitation, I may state that Koert Meelhoorn has made his academic career within the core of computer science. IT and ICT are more recent descriptions indicative of different perspectives of the field. And now informatics serves as an umbrella for a steadily increasing family of specializations, including computer science. Informatics as an academic discipline is relatively young. Its birth date is hard to determine, but it won't be much more than 64 years. That is around the age of today's Erasmus Medal winner. For all the members of the informatics section, it is a clear and most important sign of academic maturity of our field that the medal is awarded to a representative of informatics. And all of us are keenly aware of the implicit achievements of my predecessor, Herman Maurer, who nominated Koert Meelhoorn and made the case within Academia Europaea. Without doubt, Koert Meelhoorn represents the strength of European informatics research, not only by being a very effective and influential specialist in his field, but also by playing a key role in establishing a functional academic structure. The Max Planck Institut für Informatik in Saarbrücken serves as an iconic example of Meelhoorn's institutional contribution. For many years, informatics featured a competition or rivalry between three approaches to the field. Algorithms and complexity, that's the first. semantics and programming methods, that's the second, and networks and systems. To some extent, the awarding of this medal settles this rivalry. Yes, we all agree that without the ability to invent significant algorithms, there is no fundamental incentive for the development of new program notations, and not for analyzing their meaning, the key challenge of semantics. And equally importantly, the conception of new algorithms constitutes a necessary driving force for the development of new computer architectures. This driving force is represented in a remarkable manner by Peter Shor's factorization algorithm for quantum computers. That single algorithm constitutes a major inspiration for the development of practical quantum computing, a worldwide effort that catches the imagination of a steadily increasing number of researchers. I will now briefly sketch Kurt Meilhoorn's contribution to informatics. Appreciating his work requires a framework of computer science terminology which seems to be less known to the general public than the basics of astronomy, cosmology, genetics, and medicine. Meilhoorn's field centers around the following notions. First of all come algorithms. An algorithm is an abstraction of a real or imagined computer program for a real or speculative or even entirely hypothetical computer. Algorithms support the abstraction level needed for academic research. Next to algorithms, there are their implementations, still understood within a theoretical framework. The implementation of an algorithm can be analyzed in terms of a range of performance criteria. Computation time, which includes countings of numbers of steps, memory requirements, correctness, either in principle as a matter of logic or statistically in terms of a probability of failure. And very importantly, the performance criterion of energy consumption. These forms of analysis constitute a part of theoretical computer science referred to as analysis of algorithms. However, a mere theoretical implementation of a sophisticated algorithm will not make your supercomputer, laptop or smartphone work. What is needed is a realization of the implementation in a software production environment able to deliver software for widely used computing platforms. In order to develop coherent families of useful programs, specialization and focus around relevant teams is needed in such a way that dedicated software libraries can be constructed. In this aspect, Kurt Meilhoorn has been effective and influential in structuring the algorithmic part of software engineering. Starting with the Library of Efficient Data Types, developed in cooperation with Stefan Neyer in the 80s, he proceeded with the development of a software library for computational geometry, a library for the analysis of curves and surfaces, and a library for symbolic approaches to linear programming. The programs of these libraries have found widespread use throughout technology. Using software engineering terminology, Kurt Meilhoorn stands out as an influential software architect. However, Meilhoorn has always been working from mathematical first principles with a fine taste for analyzing problems at precisely that level of abstraction where a path towards further progress can be found. The majority of AE membership consists of academic professors, and you may be happy to know that Kurt Meilhoorn has always been very active in teaching. He supervised some 65 PhD students, many of whom have made research careers, and he wrote 4 textbooks. There is no sign of a slowdown of Meilhoorn's research in recent years. On the contrary, a remarkable range of very sophisticated algorithms with attractive complexity properties have been developed by him and his team in the last 5 years, dealing with topics as diverse as isolating zeros of real-valued polynomials and computing approximations for equilibria in market economies. I thank you for your attention. Could you please come to the front?
Dear Jan, many thanks for the kind words. Ladies and gentlemen, I feel deeply honored by this award. The ceremony and my list of predecessors makes this very special. I want to applaud the prize committee for its wise decision. I've set myself 3 goals for this talk. And I'm a bit nervous, and therefore I wrote down the first 5 minutes. First, I want to give you a better understanding of what informatics is about. I assume that you're convinced that informatics is useful and that it has significant economic impact. But I also assume that you know very little about informatics as a scientific discipline. So this is my first goal, to bring you informatics as a scientific discipline closer. Second, I want to give you an impression of my work, and I hope I can bring across why I am so fascinated of the field. Third, I hope that the talk is also a bit entertaining and that I make you smile a few times, and I succeeded once, and I should succeed 2 more times. So here is the outline of my talk. Yeah, these are, if you're interested in the slides, they're available on my homepage. So the outline is, first I will remind you that information technology has changed the world, and I will give you 3 examples. Then I talk about early fascination. Why did I study computer science? Then in the main part of the talk, I will first explain the terms algorithms and program. I talk about laws of computation. Laws in the sense of how physicists use the word laws. Physicists discover laws of nature. We discover laws of computation. I talk about connections to other fields. Computer science has established connections to many other fields in recent years. And then I talk about the interplay of theory and practice and mathematics and engineering. I like to call myself a mathematician in the morning and an engineer in the afternoon. Yeah, and I will talk about this interplay. And then at the end, I have 2 slides where I attempt to look into the future. So information technology has changed the world. One can probably even use the word it has revolutionized it. And I give you 3 examples. We all use mobile phones. And I'm still fascinated by the fact that I get off a plane, I turn on my phone, and 2 minutes later I can be reached. It means that there is a system. I mean, there are hundreds of millions of mobile phones on the world. And so that means the system behind it, it knows where all these hundreds of millions of phones are at any point of time. I find this amazing. Or the second example, we all use search engines. If you type Kurt Melhorn into Google, it will come back and say it knows about 150,000 documents containing the words Kurt and Melhorn, that among these 150,000 documents, the following 2 it finds most relevant, namely my homepage and my Wikipedia entry, I agree. I would say these are the most relevant documents among this 150,000. And then it took 0.3 seconds to produce this answer. Now again, it's an amazing achievement. Third, navigation systems. I remember when I used to use maps to find routes, and now I have these systems which do it for me and much better than I ever was able to do it. Early fascination. So I'm in a certain sense the oldest German computer scientist. Why? Well, computer science was introduced as a field of study in 1968 in Germany, and I started to study in 1968. It was always clear to me that I would study mathematics. Not that I knew what a mathematician would do. The only mathematician I knew were my high school teachers, but nevertheless it was clear to me that I would study mathematics, and that's what I did. Mathematics and physics. And one of my friends from high school told me, there is something new. We should also go there. I had spare time, so I also went to the computer science class. Again, I had no idea what informatics is about. I had never seen a computer, except on pictures. The lectures in mathematics and informatics were very different. The math lectures were polished. There was even difficulty. It was clear that we are entering the basement of a large tower, and that everything would build on it. And this instructor had the material on its fingertips. The informatics lecture was rough. The difficulty was very uneven. Some of the lectures were trivial. Some of the lectures were very difficult. Some of the lectures, I'm still sure, not even the instructor understood. The instructor, by the way, was F.L. Bauer, who is one of the founding fathers of German computer science, an excellent scientist. The picture on the left, by the way, shows me and my wife in '73. My wife sits here in the front row. But what F.L. Bauer understood was he was convinced, and he convinced us that we are entering a new world. That he couldn't describe this world, but he was sure that we were entering a new world with many new possibilities and chances. And he certainly convinced me. So what was early fascination? Formal languages. I was intrigued by the idea that one can define languages without any ambiguity. That you can define the syntax, so which sentences belong to the languages and which sentences do not belong to the language, and the meaning of a sentence in a precise way. By the way, a book by Hermann Maurer was the book which I read for formal languages and which influenced me a lot. Programming languages are the languages for specifying computations. F.L. Bauer in his lectures used a programming language called Algo 68, Algorithmic Language 68. As the name says, the definition of this language was finished in 1968, more precisely in December. And he gave us the book, which is a 150-page book to read in January. Remember, I was a first-year student. He gave us this book to read. This book is the most complicated book that I ever tried to read. I never made it beyond page 40 or so. And I know nobody, except the authors who read it to the end. But it was, F.L. Bauer, probably to the students who were not so good, it was a crime. But for the good students, and I belong to the good students, it was a challenge. And I think I grew up with this challenge. Algorithms and programs. So what is an algorithm? An algorithm is a step-by-step procedure for solving a certain class of problems. And I give you two examples in a moment. The name comes from Al-Khwarizmi, who was a Persian mathematician in the 9th century. And he wrote a very influential book, the compendious book on calculation by completion and balancing. So this is one of the first books about calculation. Yeah? You could call it a computer science book. Yeah? And the name algorithms is derived from his name. So here are my two examples. The first one you all know, cooking recipes. Cooking recipes are in principle algorithms. Yeah? And here I have one for calf's liver. It starts out what are the ingredients, and then it gives you step-by-step instructions on what you should do. Rinse the liver to remove any traces of blood, discard the membrane and any tough veins, cut crosswise, cook onions over moderate heat for 1 minute, and then it goes on. Cover skillet and continue to cook until softened and golden brown. So it tells you when to stop, yeah, when it's softened and golden brown. And it warns you that this will take about 10 minutes. Yeah? So this leaves very little. The inventor of the recipe is the programmer, and the cook is the machine. Yeah? The cook executes the program. Let me give you a second example, which maybe most of you learned in high school, you talked about solving quadratic equations. And maybe some of you were taught you should solve them by trying different, but some of you were also taught an algorithm it wasn't called an algorithm. And I want to go through this algorithm in somewhat more detail. So here is a sample equation, x squared plus 8x minus 9 equal to 0. And it says write the equation as x squared plus bx plus c equal to 0. So the b is the 8 and the c is minus 9. It says move the constant term over to the other side. So the minus 9 goes to the other side and becomes a plus 9. Then it says take the b divided by 2, square it, and add it on both sides. So 8 divided by 2 is 4. You add 4 squared on both sides. It says write the left-hand side as x plus b over 2 in brackets squared. So we have x plus 4 squared here. Simplify the right-hand side. So we get 9 plus 16, 25. If the right-hand side is negative, stop. There is no solution. Otherwise, remove the square on the left-hand side. Replace the right-hand side by plus or minus square root of whatever there is on the right-hand side. And then move the constant term from the left-hand side to the right side. And amazingly, this algorithm is in Algorithm's book. Yeah? In Algorithm's book, it's discussed how to solve a quadratic equation, and this is the algorithm he gives. Both algorithms are for human computers. For example, here you need to know if you move something to the other side of an equation that it changes sign. Programs for real computers are much more detailed. Yeah, but in principle, so an algorithm is a step-by-step procedure for human consumption. Programs are for consumption by computers. Let me come back. So the important thing about an algorithm is that it can be executed mechanically. There is no need to think when you execute an algorithm. Yeah? You just follow the procedure step by step until you arrive at a solution. And what you see in this picture is the computer on which I learned programming, the Programmierbare elektronische Rechenanlage München, Programmable Electronic Calculator Munich. It was built by the electrical engineering faculty at the university and was used for teaching us programming. I would say in this first 2 years of study, I had 3 insights, and those insights made me change major. Yeah? I turned from a mathematician into a computer scientist. Well, I said I'm still a mathematician in the morning. So the first insight what was that intellectually demanding task can be mechanized. So I learned in my first year an algorithm for computing shortest path between any 2 locations in Europe. Let's say between here and my home in Saarbrücken. Yeah? When I went on vacation trips, I had planned trips using maps. And this is a demanding task, yeah? Finding the shortest connection between, or the fastest connection between 2 locations. And I learned that this can be mechanized. It was an eye-opener. Secondly, humankind has always used machines to amplify muscular power. Yeah? A crane is used to lift heavy material to the fourth floor. Yeah? Computers amplify brain power. Yeah? That's very different from all the machines before. Computers amplify brain power. Third, algorithm design and programming, I felt, is an act of creation. It's not only a creative act. Yeah? You create something new, a program, like you create a paper or something. No. I mean, really, it's an act of creation. You create a program, and when it executes, it consumes inputs, it produces outputs, it interacts with its environment. It's almost a living thing. And in this sense, I mean, programming is an act of creation. This fascinated me a lot. So much about why I became a computer scientist. Now I come to laws of computation. Physicists discover laws of nature. Computer scientists, informaticians. I should say this. So informatics is usually the word for my discipline, which is used in Europe. And in most other parts of the world, it's called computer science. And I call myself sometimes a computer scientist, sometimes an informatician. Okay, so we discover laws of computation, in particular, limits of efficiency for performing certain tasks. So we ask ourselves, can a certain task be done faster than so? So the way we measure efficiency is in terms of time, the number of basic steps that are needed to compute a certain result, and space, number of symbols to store intermediate results. There is a fundamental difference between time and space. Time cannot be reused. Yeah? A time step, time advances, but space you can reuse. Yeah? You erase a symbol and you write down another symbol. Yeah? Space can be reused. So I want to discuss one limit of computation because I have chosen this limit not because it's particularly important, but because I can explain it in 5 minutes and because I was one of the discoverers. So I show here a computer chip of an old computer chip of 20 years ago. Oops. No, forward. Okay. So on this chip there are millions of transistors, and here on the left lower corner there is something called multiplier. So what this thing does is, oh, by the way, the whole thing is about 17 by 18 millimeters. This multiplier occupies about 3 by 4 millimeter of space, and it multiplies numbers in 5 microseconds. Is this good? Yeah, should one be impressed that a chip which has 3 by 4 millimeters can multiply numbers in 5 microseconds? Can this be done much better? So we have two complexity measures, namely the area of the circuit, how large it is. This was 12 square millimeter. And the execution time, how long does it take to carry out the multiplication? Now there are many different circuits for multiplication. And an observation is there are circuits that are fast, but then they are large. There are circuits that are small, but then they are slow. Yeah? So there are fast circuits, but they are huge. There are small circuits, but they are slow. Is there a circuit that is small and fast? It's a natural question to ask. And the answer is no. There cannot be such a circuit. Let me be more precise. So what I've shown you here on this diagram, so I have two axes, one for the time t required for multiplication, the area required for the circuit. Any circuit corresponds to a point in this diagram. So large circuits would be here to the right, large area. Circuits which are fast would be down here. Circuits that are slow would be up here. So a circuit here would be slow and large. A circuit here is large and fast. A circuit here is small and slow. And what this law of computation says is there is a curve below which there are no circuits. Every combination of space and time which is in this red region is impossible. And on the positive side, there is a slightly shifted curve, and everything above it is possible. And there is a region in between where we don't know yet. Yeah? So this is a law of computation. It tells you exactly in this model of integrated circuits how fast you can multiply numbers. Let me proceed to connection to other fields. It started out with electrical engineering, circuit design, embedded systems, and the natural sciences, high-performance computing. But now there are also intensive connections to linguistics, things like machine translation, speech recognition, information retrieval, to biology and medicine, bioinformatics, but also computation performed by nature, and I give you an example in a moment. By the way, the items which are highlighted in blue, I have worked. So on these connections I have worked. Economics, business processes, game theory, algorithmic economics. I want to give you an example of computation in nature. So this is a paper which was published by Nagakaki and Yamada, two Japanese researchers, and a Hungarian researcher taught in Nature in 2000. They studied a slime mold called Physarum. The slime mold is everywhere. If you go to the woods, you will find it. It can grow cells, fairly large cells the size of a hand. A single cell the size of a hand. This cell will have many nuclei. You can treat this slime mold cruelly, in the sense you can cut it into pieces. If you put the pieces next to each other, they will unite again and form a single cell. And it can form networks. And the way this research started for me, I watched TV. I'll show you the video in a moment. And they were reporting that this slime mold can compute shortest path. So they performed the following experiment. They built a maze. You see the maze in yellow. And they made sure that the slime doesn't want to live in the black parts. Yeah? And they covered this maze uniformly with this slime. Then they provided food at two places, and you will see this in the video in a moment. And then the slime first retracted from the dead ends, and then after about a day or half a day, it had retracted to the shortest path connecting the two food sources. And they reported in this science magazine on TV that this experiment was repeated with 20 different mazes, and each time the slime found the shortest path. I was a bit insulted. This slime doesn't have a brain. Yeah? I teach shortest path algorithms to my students. I've written papers about them. Yeah? And now here comes the slime, and can also do it. Yeah? Let me show you the video. And maybe can you turn down the light for the next 1 or 2 minutes, even more? Okay. Oh, then maybe not. Okay. So here you see Professor Nagakaki, how he puts the slime on the maze. Yeah, this yellow stuff is the slime. He puts it on the maze. Yeah, he takes off small pieces, he puts it on the maze. Then now you will see how these pieces unite again. Yeah, and then cover the maze uniformly. Now comes the food thing. Yeah, now comes the food, and he supplies food at places A and B. Yeah, you may already guess what the food is. It's oatmeal. Yeah, then on the next, now you will see that this slime really loves oatmeal. Yeah, he starts eating it, grows over it. Then you will see how it moves food through its body in waves. Then you already see that it starts retracting from the dead ends. Yeah, I'll let you watch a little bit more. Yeah, again, how it retreats from the dead end. And on the edges of the maze, it even straightens out. And after half a day, it has found the shortest path. How do I stop this? I think here. No? Here. Okay, where is the talk? So let's go back to the talk. Yeah. I was really intrigued. Yeah. So the next morning I read my daily newspaper, and on its science page they report also about this experiment, and they gave references. So on when I went to the university, I digged out these references. I told a few colleagues at lunch that I saw this video, and I got them interested. Yeah? How does this animal do this? And we found a paper which was published in 2007, which introduces a mathematical model of this slime. It says this Physarum is a network of pipes. Yeah, I have a sort of an abstraction here, a network of pipes. And there are concentration differences of nutrients in the different nodes of this system, yeah, indicated by the different colors. And these pipes have different width and different length. And the flow of liquids is determined by the concentration difference at the endpoints. The higher the concentration difference, the more the flow. But the longer and the smaller the widths, the smaller the flow. And these pipes adapt to the flow through them. Namely, if the flow through a pipe is high relative to the diameter of the pipe, then the pipe grows. If the flow is small relative to the diameter, the pipe shrinks. Yeah, so they put this in a mathematical model. I had the equations on this. I should mention this. I gave a practice talk last week to the administrative staff of our institute, and they forced me to remove all the formulas from the slides. So thanks to them, there are no equations anymore on the slides. So. Yeah, and about 2 years ago, Vincenzo Bonifaci from the University of Rome and Girish Varma from Tata Institute in Bombay, we were actually able to prove that the network converges to the shortest path in this mathematical model, namely the diameter of the tubes which are not on the shortest path converges to 0. And now I understand this slime a lot better. I don't feel insulted anymore. But I'm intrigued that such a simple dynamics can exhibit such a complex behavior. Yeah, I said already I like to call myself a mathematician in the morning, an engineer in the afternoon. As a mathematician, I work on problems of a fundamental nature that are intrinsic to the field, for example, laws of computation or new algorithms. And on problems that come up in applications and that are too hard for engineers. On the other hand, as an engineer, I turn algorithms into programs, I design and build systems, I turn ideas, mathematicians have only ideas, into working systems, and I identify the need for further theory. And I want to give you an example of this. Jan mentioned this already, the work on the library of efficient data types and algorithms, which is joint work with Stefan Neher and also Christian Uhrig. So I became a professor in the mid-70s, and I taught courses on algorithms. And when I met former students, I of course asked them whether they are using any of the stuff that I taught them. And I always got very polite answers. Yeah? Namely, the problems come up, but my boss didn't give me the time to implement any of the sophisticated solutions that you taught us. We always go for the simplest solution. And I concluded from this that writing books and articles does not suffice. Yeah? But that I must, if I want to have real impact, I must turn the knowledge of the field into software that is easy to use. Yeah? People use only things that are easy to use, that are efficient so that they can solve large problems, and which are correct so that people can rely on the software. Yeah? The system that we designed is called LEDA. You see the book and an example run of the system. It's in use at thousands of academic and industrial sites. I founded a company which markets it, and it still sells. The fact that I founded a company, the original motivation was of course that I wanted to become rich, but now I see the feedback from customers that paid for it is extremely important. Yeah? Academics are nice. People that paid for it, they tell you the truth. Now, our programs were easy to use, they were efficient, but some of our programs were incorrect. And this almost ruined my reputation, because I had announced that I would build this library, and I had announced that the algorithms in there would be easy to use, correct, and efficient, and then some of our programs were incorrect. Yeah, what had gone wrong and what did we do about it? We had followed the state of the art. Yeah? It's not that we were sloppy. We had followed the state of the art. But, okay, we implemented algorithms dealing. One part of the library is about algorithms that handle geometric objects. And there was a big gap between what the algorithm designers assumed and what real computers provide. Namely, the algorithm designers assumed that they can compute with real numbers in the sense of mathematics, and real machines provide only a very poor abstraction of the numbers of mathematics. So there is a big gap, and so simply there was no scientific basis available for geometric computations, and we and others created a basis over the past 20 years. That's why I'm now also working in computer algebra, because this is needed for implementing geometric algorithms. And then the other thing is we made mistakes. Yeah? We started with correct algorithms, but we made mistakes in implementing them. And of course we followed the state of the art. We tested our programs. We tested them extensively, but for some of our programs, what does it mean to test a program? It means you run it on an input for which you know the output. Yeah? And then you check whether your program gives the correct answer. Yeah? Now, we wrote programs that were more efficient than any other program around. Yeah? So we could run it on instances on which nobody ever could run it. Yeah? So we just didn't know what the answers could be. Yeah? We could test it on small examples, but for some of our programs, we had only a very small number of small examples. Yeah, today LEDA I think is a main source of my reputation, because what did we do we adopted a new design principle called Certifying Algorithm, and I will spend the next 10 minutes talk about this. So the problem is the following. You write a program for a certain task, you feed it an input, I call it X, the program returns an output, I call it Y. Now, how can you be sure that indeed Y is the correct output for X? As a user, you have no way to know. Let me assume for the moment you are the owner of a construction company, yeah? The boss of a construction company, and you want to bid for a construction project. Yeah? You ask your assistant to come up with the right bid. Yeah? Your assistant looks at the project and comes back 2 weeks later and says 3,459,213 euros is the correct bid. And we will make a 10% profit on this. Of course, as the boss of the construction company, you will say, how did you arrive at this number? Explain it to me. Yeah? You will not just accept this number at face value. But when we use computers, we almost always do this. Yeah? Computers come back, give us something, and we accept it. My tenet is that programs must prove their answers in a way that is easily checked by their users. Yeah? Programs should also be forced to come back with an answer and a justification, a convincing justification why this is the correct answer for a particular input. So if you take this proposal seriously, you arrive at something like this. You have a certifying program, which again gets X as an input. It outputs the Y as before, but in addition it outputs a W. And what is this W? W is, I call it a witness. It's convincing evidence that Y is the correct output for X. And then a user of this program can inspect the W and either say, yes, I'm convinced, or say, no, I'm not convinced, I reject this. Or even more elegantly, you write a small program again, I call it the checker program, which does this task for you. Yeah? It looks at the witness, the output, the input, and says, yeah, this witness is convincing, and you should accept the Y. Or it says, no, this witness is not convincing, reject it. Let me give you an example. And I will come back that I check a program by another program. Yeah, why should I trust the other program? Yeah, but we come back to this. So here is an example where I learned a lot. So I need to introduce a notion of mathematics, a graph that's something like this. It's an abstraction of a road network. There are road crossings, those are the dots. And there are roads connecting these dots. Yeah? And here, the roads only cross at the endpoints, only at intersections. So this is a planar drawing of a graph. Here is again a drawing of a graph, but here there are two roads. They cross here, but this is not an intersection. Yeah? They cross accidentally. It's badly drawn. Yeah? You could draw it like this. You could take this edge here and draw it like this, and then it would be a planar drawing of the same graph. But there are some graphs which cannot be drawn without crossings, and the smallest ones is this graph called K5. It's a graph on 5 vertices, where any 2 vertices are connected. And this graph on 6 vertices, 3 on the top, 3 on the bottom, and every vertex on the top is connected to every vertex on the bottom. It's, the K stands for Kuratowski, and Kuratowski proved in 1910 that every non-planar graph of a certain size, namely with at least 5 vertices, contains one of these 2 vertices, one of these 2 graphs. We put in LEDA an algorithm which tests graph for planarity in 1993. It was implemented by one of my students. And it was widely used. I don't have the time to explain why it was widely used. But in 96, somebody sent us a graph together with a planar drawing. And our program declared that this graph is non-planar. Yeah? So our program was incorrect. The letter was addressed to Stefan Neher, and he came with this letter to my office and said, Kurt, this was your student. You fix it. So I looked at the program. I found the mistake. I fixed the mistake. it now worked correctly on this instance and all the other examples that we had. But then Stefan and I started discussing, I mean, okay, we removed this error, it now works correctly on one more example. Yeah, and we said, it's not the student who is to blame. Yeah, it's we who are to blame, that we asked him to write a program which answers a complex question, namely, is a graph planar or not, by just saying yes or no. It's the wrong specification. We should have asked the student to write a program which gives a proof. Yeah? And let me run a demo for you how this program is now. So what I do here is I generate a graph with, I think, 11 vertices and I think 19 edges randomly. Yeah? So I choose 19 pairs of vertices and I put down an edge. Then I test it for planarity. And the old program would just output this graph is planar or this graph is non-planar. Yeah? There is an edge crossing here. Yeah? But this can be removed by drawing, apparently, by drawing the graph differently. Now the new program says, then there's, do you want to see a proof? If yes, click done. Oh, I wanted to click done with the pointer, but that doesn't work. Yeah, here's the proof. It morphs the graph into a planar drawing. And here's another graph, and it says it's non-planar. Should you believe this? Well, do you want to see a proof? And it shows you a proof. It shows you a K33 contained in this graph. Here are the 3 red vertices, the 3 blue vertices, and every red vertex is connected to every blue vertex by a path. And these paths are edge disjoint. Yeah? So here to this, and so on. Yeah? And if you believe, well, if I have 5 minutes time, I could convince you that K5s and K33s are not planar. Yeah? It's a very easy exercise. Let's see a few more examples. Yeah? So this is not planar. I need to wait, I think, 5 seconds. You want to see a proof? And again, here is a K33. This graph is non-planar. I generate random graphs. I have no idea what comes up, yeah? Whether they are. I'm running a live demo. Yeah, I've always run a live demo here because I'm absolutely convinced that nothing can go wrong. Yeah, this is, one last thing. This is planar, and so the program will morph it into a planar graph. Let's go back to the talk. We're almost done. Yeah, history. I do not claim that I invented the concept. It's rather old. In fact, it's in Al-Khwarizmi's book. Yeah? He talks about multiplication of numbers, of long numbers, and then he explains, in Germany it's called Neuner Probe. In English it's called casting out nines. So I was taught this in elementary school. When I do multiplications of long numbers, I should also do the digit sum of the 2 operands, yeah, Quersumme. You sum up all the digits until, and again until you get a number between 0 and 9. You do this also with the result, and you check whether the multiplication is correct for the digit sum. There is also a casting out 11, where you do alternating digit sums. Yeah? And if your multiplication passes those 2 tests, it's very likely to be correct. The extended Euclid algorithm is what I do claim is that Stefan and I were the first to adopt the concept as the design principle for a large software project, namely for LEDA, and recently I wrote an 80-page survey on the subject. Now here is an important who checks the checker. Yeah? I said we have this program over here, and what it does, it checks whether this program worked correctly by looking at the witness. How can I be sure that I get this program right? And what I said up to 3 years ago when I gave this talk is that these programs here are so simple, we get them correct. Yeah? But even simple programs one can get. Okay, today's answer is Checkers are so simple programs that we can prove their correctness using formal mathematics. What is formal mathematics? So mathematics is usually carried out in natural languages, in English, in German, but it can also be carried out in formal languages. So mathematics is carried out in a formal language without any ambiguities. Yeah, and proofs, how are proofs usually checked? Proofs are usually checked by another mathematician reading the proof, or by students listening to the professor, or you read a textbook and you check the proofs, and so the proofs for the most important theorems are checked over and over again, and even, mathematical proofs contain these lines clearly, as one easily sees, and then details are left out. And if you do formal mathematics, you cannot leave out any details. Here on the right-hand side is a piece of formal mathematics. I will not go through it. You have to do definitions very carefully. You have to talk about things which are obvious to a mathematician, that if you have a pair of objects, you can also look at this pair as a set of two elements. Conversion from a pair to a set, that's trivial for a mathematician, but here you have to spell it out, you have to say it. And you have to say, I want to prove a theorem, what I use is the two definitions above. But you can also say something and ask the machine to help you in doing the proof. So the system that we use was developed by Larry Powson and Tobias Nektov. The proofs are machine checked, so you need to trust only a very small. And there is always something you need to trust. There is a small kernel of Isabelle Hall which you have to trust. So what we do now is we formally verify the witness property, namely, if a graph contains a Kuratowski subgraph, one of these K3 or K33 or K5, then it's non-planar. We prove the termination of the checker program, meaning that this program here always holds and either returns acceptance or reject. And third, that the checker program is correct. So meaning if W is really a convincing evidence for Y is the correct output for X, then the checker will accept it. So what we have now is, if one of our formally verified checkers accepts a triple XYW, we have a formal proof that Y is the correct output for X. This is, I think, the highest achievable trust in the moment, and a way to build large libraries of trusted algorithms. So if I would have to redo later, I would now do all the checkers and formally verify the checkers as we have done here. This is joint work with, in particular, my PhD student, Christine Riscala. The last 5 minutes, I wanted to say something which impresses also the computer science colleagues in the room. 2 slides for looking into the future. What we will see, trends from information to knowledge. None of the current search engines can answer the following question. Who was the coach of the Scottish soccer team when Germany won the world championship in the 70s? No, but you can answer this question given, let's say, half an hour. You would go to Wikipedia, you would look up when Germany was world champion in the 70s. You would then go to the webpage of the Scottish soccer team, and it probably lists the coaches of the last 30 years, and you would have the answer. What my colleague Gerhard Weikum does in the moment, he builds a large knowledge base where he extracts knowledge from first Wikipedia, but now also newspaper articles and so on, and he builds a large knowledge base, and his system can answer this question already. There is also a system developed by IBM called Watson, and it won a quiz against a human player called Jeopardy, where you have to answer questions of similar to the one I just named. Big data and machine learning is a big trend. How can you make computer programs better by a large number of examples? For example, machine translation is done very differently now and 30 years ago. 30 years ago, the main approach to machine translation was to study the grammar of languages very, very carefully. Yeah? Now, one uses a lot of data. There are large corpuses of excellent translations out there. Yeah? For example, the European Union produces papers in 5 or 6 languages. Yeah? And these are done by experts. Yeah? So maybe your sentence was already translated by an expert and you only have to look it up. Or a sentence very similar to the one you want to translate. Yeah? So modern translation programs use a lot of big data. We're going to see autonomous systems. Yeah? The self-driving car is an example, which is produced at several universities, produced by Google, is produced by Mercedes recently. So the first drive by a Mercedes car about 100 years ago, more than 100 years ago now, was from Stuttgart to Pforzheim, and they, as a public relation event, they repeated this trip recently, but now the car drove autonomously. Yeah? And of course, all of this, security, privacy. So many of the computer systems which we use now, for example, the operating system which runs on this machine, was designed for a group of friends. Yeah? For a group of people that trust each other. They were not designed for people who want to exploit the system. Yeah? So security, we need to redesign many of our systems with this concept of security in mind. Many of the new developments, they threaten our privacy, and we need to work on this. We need to work on this from the society point, from the legal point, but also from the computer science point. We have a center in Saarbrücken, of which I'm a principal investigator, a center for IT security, privacy, and accountability. Let me come to my last slide. Aha, oh, there's a last slide. A course that I'm teaching in the moment. It's called Ideas of Informatics, an introduction to informatics for non-specialists. So German university have something which is called Studium Generale, so where students have to learn things beyond their major and their minor. The goal is informatics literacy. So what I do is I present concepts and their applications. So I talk about cryptography and electronic banking. I talk about shortest path algorithms and navigation systems. I talk about machine learning and automatic translation. I've taught this course now 3 times for the students in Saarbrücken. In this winter term, I want to offer it as an online course for all German-speaking students, and I'm still trying to find out how I can give all students in Germany credit points for taking this course with me. Yeah? If you have any ideas, come to me and let me know. Thank you for your attention, and I hope you enjoyed it a little bit, and you don't think that it was a mistake to give the medal to me.